Okay, welcome back to Biostats. I'm Dr. Mark Holder, and today I'm going to talk about probability. So, Chapter 5 is on probability, and it's a really important concept not only for understanding the rest of the material in the course, but also because probability is a core part of statistics and modeling of scientific processes, and particularly in biological modeling. So, it's important to understand probability in its own right. Not supposed to start a lecture with an apology, but I must say that this first lecture is really heavy. First two lectures are really heavy on definitions, and that I know can be a bit tedious, but it's really important to have in your head the actual definitions of the terms we use and to be able to think about how to express probability concepts clearly. So we've just there's no avoiding going through some definitions here. Okay, so the definition of the probability of an event is the proportion of times that an event would occur if we could repeat a random trial many times, essentially an infinite number of times, so as the sample size went to infinity. This is what's called the frequentist definition of probability that we're going to use for this course. There is another definition, a Bayesian definition of probability, that I'm going to discuss briefly in a module for Chapter 5, but it's not going to be the dominant definition we use. So this one on the screen now is the most important one for you to know for this course. So let's just break this down a little bit and focus on a few words. Statistics has a nasty habit of using a lot of words in everyday English in very specific ways, so it's important to understand exactly what we mean in the statistical sense when we use these words. So proportion is just the relative frequency. This one there's no surprises here. This is the relative frequency that we've seen in earlier chapters. It's you can think of it as a fraction of the time, so it's going to be a number between 0 and 1, the proportion of times an event occurs, if we could repeat a random trial. So what is a random trial? A random trial is it could be an experimental or an observation, any phenomenon that can be repeated but have a differing outcome over the repetitions. So it's important to realize that a random trial doesn't just discuss things that are entirely random. You could do something like your running speed in a race that's affected strongly by how fast you are, but there's going to be some variation race to race, and so that variation means that there's enough uncertainty that we can think of that as a random trial, even though it's not entirely random. And what do we mean by event? An event is just the probability jargon for a possible result of a particular trial. So we can think of all the possible results of a random trial, all of the possible outcomes, and we have a name for that, the sample space. So for instance, this table shows a bunch of random trials and what their sample space would be. For a standard coin, we say that it comes up either heads or tails. If we roll a standard dice, 1, 2, 3, 4, 5, or 6 are all the possible outcomes. So that the sample space determines what the value of an event can be. In the ABO blood type, it would be the phenotypes at that trait, A, B, or O. You can have numerical sample spaces. So for instance, the clutch size, number of eggs in a nest, could be any non-negative integer. So it's important to understand where the possible values for a trial are. Height can be any real number, so that's a continuous numerical variable. Or something like wealth, you can have negative net wealth, so that can be any real number. Obviously, there are limits to what these biological limits to what these variables can have, but we can think infinitely. We can think of the sample space as being effectively infinite because it's a priori we don't know what the upper limit or the lower limit is. And another thing to realize is that we talk about an event being the result of a trial. An event can be defined to be any kind of subset of the sample space that you're interested in. So we're going to see that in the next few slides here. It's not just the simple results that you see listed in the sample space, it can be combinations of them. So it's crucial to understand these concepts because you can't really understand the meaning of a probability statement that you see unless you know what event is being expressed. So if you see some probability as 0.35, you got to know 0.35 of what event. You have to know what the other options were. You have to understand the sample space of the trial. And often you need to understand the background model that's being assumed to give you those numbers, or at least have a sense of what that model is. And this is a tricky part that often confuses people when dealing with probability notation is that frequently we don't clearly express the background model. It's often in a textual description that surrounds the probability statement. So you really have to be reading the question and not just looking at the notation. You have to understand what's being assumed. So we'll walk through how that works. So one of the things I posted on Blackboard is this list of probability rules, and it looks very terse and it may look intimidating, but we're going to walk through these in the next 3 slides. So the important thing is sort of understanding how to read them and use them effectively. And so that's going to take most of the time in this chapter. So and I should also mention we're never going to quiz you on like what is Rule 5 or Rule 6. You don't have to memorize these. We just made up the numbering just to walk through them in a lecture order. The important thing is to understand how to use them, not this numbering system. So don't worry about that aspect of it. Okay, so rule 1 is that the probability of an event is always between 0 and 1 inclusive. That means I include the endpoints there. So for instance, if we see something like the probability that an event of a coin flip is heads is equal to 0.5, what that means is we expect half of the coin flips to be heads and half of them to be tails. The probability that a dice gives you a 7, well, that's impossible on a standard dice, so that would be a probability of 0. So 0 means an impossible event. Or what's the probability that a dice roll is less than 7? Well, that's a probability of 1, right? Because in a standard dice, all the rolls are going to be less than 7. So those bounds of the probability range, 0 and 1, mean impossible and certain, respectively. And if you ever see something that says like probability of some event, like a coin flip is 2, and that the probability of that event is negative 1.5 or negative anything, you immediately know that you've made a mistake. And so we give lots of partial credit in this class, but when we see probabilities that are outside the range of 0 to 1, it's hard to give a lot of partial credit for that because it makes very clear to the grader that you don't understand this really important concept in probability, that it is the relative frequency of an event. So the most frequent events can only happen 100% of the time, and that would be a probability of 1. And the least frequent happen never, that's 0. So they've got to be within those ranges. Okay, now getting back to some definitions that are going to be crucial to understanding how to correctly apply the probability rules. We say that two events are mutually exclusive. They exclude one another if they can not both occur on the same trial. And it's really crucial to have this same trial notion in your head here. So if A and B are mutually exclusive, then by definition their probability of them both happening on the same trial is 0. And we would denote that with either the and statement. Sometimes you'll see just a comma. The probability of A comma B is read as the probability of A and B. Or you can define a higher level event. You can say the event C is the event that both event A and event B occur, and that probability is 0. So these are all ways of saying that two things are A and B are mutually exclusive, right? So you can think of this term mutually exclusive just sort of as it sounds. They exclude each other. If A happens, then B can't happen. If B happens, then A can't happen. So each one excludes the other one. All right, so why do we need to talk about this? Well, we need to think about sample spaces in order to apply the rules correctly. So for instance, this next rule in the probability rule sheet that I've posted on Canvas is that the probabilities of all the mutually exclusive events add up to 1, but it's not all events, it's all mutually exclusive events, and it's not all mutually exclusive events, it's all mutually exclusive events that cover the entire possible sample space. So all possible mutually exclusive events. So if you can think of the sample space being some set of events, it varies depending on the type of random trial that you're doing. It could be k events here. Then those probabilities are going to add up to 1, as long as you've broken it down into mutually exclusive possibilities that cover everything in the set. And I think of this as that something's got to happen or something must happen. Everything's the bookkeeping of probabilities got to add up so that something is certain to happen on a random trial. And it's just a question of which event. So with probability 1, something will happen. So it may seem like we wouldn't use this rule too often, but we end up using it in kind of a backhand way a lot. So for instance, think about what's this probability of rolling a 1 on a fair 6-sided die. A probability of rolling a 1 on a fair 6-sided die, well, we say, well, the probabilities have all got to add up to 1. And this is where it can be helpful to expand the notion of how we denote events. And so it's useful to think about, okay, some event I that we're talking about, what does that mean? Well, we're talking about rolls of a dice. So maybe we're going to use R as the random variable, the result of a random trial, and we're interested in whether the roll equals the value I. So in that case, with our dice, I ranges from 1 up to 6. So we do a summation from 1 up to 6, and what's the probability of each of those rolls? And that's got to be equal to 1. Now, by the meaning of the word fair here, what that's saying is that all the rolls are equal values. So all those probabilities add up to some number. So what that allows us to do from here above is things that I showed on the previous slide. What that allows us to do is take the summation here and convert it, just replace x for some unknown value. What is the probability value that when added 6 times gives you 1? And obviously that summation expands to just x plus x plus x 6 times, so that's 6x, and so that gives us 1, which gives us the probability as 1/6. So probably a lot of you leapt to that immediately, but this is actually an application of that rule too, that everything must happen. Probabilities have got to sum to 1, and so if there's 6 equal probabilities, then the probability of each one has got to be 1/6. Just a note on working with summations. I know a lot of people haven't seen this before in math class, but you can just treat this summation, as has been described in previous lectures, as it's a quick notation, a terse notation for adding up a bunch of things. But we can do the math that we've learned in previous math classes on that. So for instance, in this case, if you've got this sum of x 6 times, you can factor out the x in front. And if you factor out the x from x itself, then you're left with just 1. So this becomes a summation over 1 6 times, which is 6x, of course. Right? And so you can use the standard math. It just takes a little bit of getting used to how to work with this different notation for summations. And in general, we'll see this applied in many places in the course, where if we sum a constant value up k times, then that we don't have to think of it as a sum. We can think of it as just k times x, and that simplifies a lot of the math that we'll see. So we'll see that trick many times in the course. Okay, back to the probability stuff. Another context where the concept of being mutually exclusive is important is what I think of as the mutually exclusive addition rule. If A and B are mutually exclusive, then the probability that A or B happens is just the sum of the probability of A plus the probability of B. Okay, so this only applies when the two events you're talking about are mutually exclusive. So for instance, what's the probability of rolling an even number on a fair 6-sided die? So it's important to have the sample space in mind. Here's the sample space for a 6-sided die. It's all 6 numbers. We just went through the argument of why, because of the word fair, they're equal probable, and that means that the probability of each one of these sectors is 1/6. We've previously discussed how using pie charts is not a great way to show probabilities or quantities, but the one exception to that rule is when all the quantities are equal, then all the pie slices are exactly equal in your mind. Your eye gives you an accurate representation of what's going on. So bar charts in general are a lot better way of showing probability distributions than pie charts, but in this special case where all the probabilities are equal, then pie chart's a nice compact way of doing it. Okay, so we said what's the probability that a roll is even, so we can just define that as our event. Event A is the probability the roll is even. If we want to think about it in terms of the random variable, it's the roll is somewhere in the set of possibilities. So this symbol here means an n. So the roll is in the set 2, 4, and 6. Now you're not going to be quizzed on using this exact notation, but it's important to understand what we're saying here. We're saying that we want to know the probability that the roll is 2 or 4, or the roll is 4, or the roll is 6. So what the mutually exclusive addition rule means is that because you can't roll a 2 and a 4 on the exact same roll, those events are mutually exclusive, nor can you roll a 6. And so because of that, we can just add the probability of each of those 3 events. So 1/6 plus 1/6 plus 1/6, so it's 1/2 down here, right? We can use this simple rule of just adding up these probabilities because these three events, rule of 2, rule of 4, and rule of 6, are mutually exclusive to each other. Okay. Also note that if we think of some event A and another event called the complement, which is just the event that A does not occur, sometimes denoted not A, those are automatically mutually exclusive, right? It's not possible for event A to happen on a trial and the event not A to happen on a trial. Either one of them's got to happen. So they're mutually exclusive, and since one of them's got to happen, they cover the entire sample space. They may not be the most fundamental events in that sample space, but they do cover the entire sample space. So that means they should sum up, their probability should sum up to 1. And so if we just do a little bit of algebra, we can see how that the fact that the probability sum to 1 means that if we want to know the probability of not A occurring, we can just say it's 1 minus the probability of A. So we end up using this rule a fair amount of the time. It's just a rearrangement of rule 2. But and rule 3, so we're sort of combining knowledge from both of those things, and we end up using it to solve a lot of practical problems. Here's a problem that is probably so easy that we don't need to think about using this rule, but hopefully we'll demonstrate how we use it. What's the probability that a roll would be something other than 5? So once again, we think of the sample space. One way to solve this problem is to just think of all the rolls that are not 5, 1, 2, 3, 4, and 6. And so just add them up because those are all mutually exclusive, and that gives us the right answer. And so one of the things I should note about this probability module is some people have just really different ways of solving probability problems from the way I think about it. That's totally fine. We're not going to mandate that you solve them in exactly the way that that we solve them. So if you have a valid way to solve the problem, that's fine. Use it. Okay, so in terms of using this new rule that I just talked about, the complement rule, we were interested in what's the probability of a roll that's not 5. Well, we could think about what about the event B that the roll is 5, right? That's just one outcome. We've already talked about why that's 1/6. So if we're interested in what's the probability of not having a 5, not B, then we can just do 1 minus that probability. So we can get the same answer in multiple ways. And sometimes this subtraction method using the complement rule is a lot more efficient. So that will often save you a huge amount of time. Okay, just plugging through our rules here. I know it kind of is tedious to walk through these rules, but we'll start to solve more biological questions at the next video. The general addition rule. Okay, so what about if you have two events A and B and you don't know that they are mutually exclusive, or you know that they are not mutually exclusive? There's a general form of the addition rule that says if you're just interested in what's the probability of A or B happening, you can think of it as what we did before, sum up their probabilities, but then you subtract the probability that they both happen on the same trial. Now, if they're mutually exclusive, this probability goes to 0. If they're not mutually exclusive, it's going to be something greater than 0. So this is, in some sense, the better rule to memorize because it works all the time, even when they're not mutually exclusive. For example, what's the probability that a roll will be odd or less than 4? All right, well, we can think about those in terms of the distinct events that they entail, or in this simple case, we can just think about what are all the numbers that are odd and less than 4. 1, 2, 3, and 5, right? 1, 2, and 3 are less than 4, and 5 is odd. So is 1 and 3, by the way. But anyway, those are the relevant values for the event we're interested in. So we can just sum them up because these rolls of 1, 2, 3, and 5 are mutually exclusive, so we can just do this as a sum and we get 2/3. 1/6 4 times gives us 2/3. Okay, but in terms of using the rule and seeing how that's applied to solve the same question, the newer rule, well, we can break down that complicated event. The roll is odd and less than 4. We can break that down into what's the probability the roll is less than 4. All right, that's these three events over here, these three sort of atomic events over there. There's a 1/2 probability that it's 1, 2, or 3. Those are the numbers that are less than 4. What's the probability that the roll is odd? Well, there's also 3 events. Now it's 1, 3, and 5. 3 sort of core events that add up. Those are all mutually exclusive, so we can add those up to get 1/2. All right, what about the probability that the roll is odd and less than 4. So on the same trial, it's both. And now it's just 1 and 3, right? These are both odd numbers that are less than 4. So there's 2 of them, and that gives us 1/3. Yeah, that's supposed to be a check mark. Okay, and I've sort of chosen the colors here. We can think about blue and yellow adding together to make green. Green being the set of events that occur in both less than 4 and the roll is odd. So the answer to our problem, what's the probability of B or C, that a roll is less than 4 or odd, is we add B and C, and then we subtract off that intersection where both B and C occur. So it's 1/2 plus 1/2, that's 1, minus 1/3, that gives us the same answer we had before. So if we look at this sample space, it seems weird to a lot of people. This is a rule that confuses a lot of folks. Like, why are we subtracting off this probability? It's not that they don't count towards the event occurring. It's that 1 and 3 are counted twice. When we add up B, they're in there, and when we add up C, they're also in there. So they get double counted. So this is to correct for that and subtract them off. So we avoid double counting them and we just count them once overall. And so they do still contribute to this probability, but it's important that they only contribute once, and that's why we have to subtract off the probability that they both occur. So we'll see this in a lot of problems. Here's a more realistic problem, finally getting away from the rolling of dice. A park has 2 species of hawks in the genus Accipiter. If a birdwatcher visits a particular spot in the park, there's a 10% chance that they will see an Accipiter striatus, the sharp-shinned hawk, and a 20% chance they'll see an Accipiter cooperi, the Cooper's hawk. The species avoid each other, so there's only a 1% chance that they're going to see both of them. What's the probability that a birdwatcher will see at least one Accipiter on a visit to this park? Okay, so when we are confronted with a verbal description like this, the first rule is to try to extract the probability statements from that problem, so we can say, okay, well, the probability that striatus is seen is 0.1. So now I'm thinking of the sample space of these events as being yes and no is the sample space. So the probability that striatus is seen is 0.1. The probability that cooperi is seen is 0.2. And then there's a 1% chance, 0.1, of the probabilities of them both being seen. So striatus is yes and cooperi is yes. One thing I should point out here is often probability statements are given to us in terms of percentages, but I highly recommend that you work all your problems in terms of this proportion notation like this. So convert them from percentages to numbers from the 0 to 1 range. It's possible to solve the answers with the percentages in there, but it's really easy to mess yourself up and forget when you multiply 2 percentages. Now you're doing per 10,000 instead of per 100, and so it's much safer to work on the scale of 0 to 1. So we'll frequently just rewrite the probability statements in that format. Okay, so what's the probability that we're asking about here? Okay, maybe pause the video and work it out yourself. I'm going to advance and we'll find the answer here. There's the data that we had. We're interested in the probability that we see one or the other, so it's an or statement, the sharp-shinned or the Cooper's hawk. We don't know what that is. Well, to work through that, here's what we were given and extracted on the previous slide. Remember, we're going to use the general addition rule because these are not mutually exclusive events. It is possible to see both of these at the same time. It's not a 0 probability. So we can't use the simple addition rule. We've got to add up the probability we see a sharp-shinned plus the probability we see a Cooper's and subtract the probability that we see both. So it's 0.1 plus 0.2 minus 0.01. Right? These are these core probabilities up here. And that gives us an answer of 0.29. Frequently, we like to express that in terms of a percentage, so at the end of the problem, you can put that back into percentage form, but all of the calculations are done on the number between 0 to 1. So if we were to visualize the entire sample space of having a probability of 1, this is the event that we see either one or the other. And just to emphasize this point again, this was 10%, this was 20% seeing the cooperi, and then there's this 0.01% of seeing both of them in green. That does count towards the probability, but we subtract it because we only want it to count once. If we just add the two, we're counting that green region twice and we'll be off by 1%. Okay, let's pause for a sec from walking through the rules of probability and talk about one really important aspect that I've glossed over. What happens if the sample space of an event is continuous? So for instance, if we have a probability distribution over a variable like mass, so that's a continuous numerical variable, and really what's important is the possibilities are infinite in terms of the values of that variable, because there's an infinite number of masses, at least conceptually, when we think about the real number line. Each particular value has no probability itself. Instead, each value has what we call a probability density. So when we talk about continuous values, we're talking about probability densities. And we'll see graphs that look like this. And now the y-axis here is probability density. It's how much probability you have as you move a unit along the x-axis. So just like we can't talk about how much gold weighs, what's the mass of gold, we need to know how much gold we're talking about, what's the volume of the gold in order to tell you what the mass is. We can say that gold is dense. That means it carries a lot of mass per unit volume. So it's that in that sense, an area of high probability density, there's a lot of probability as you walk along the x-axis there. And so it's kind of a weird concept to think about. But it's a crucial concept, and when we see curves like this, we're going to see a lot of this in the course. When we talk about the probabilities from these curves, we're looking at areas under the curve, so shaded in areas. Those are actual probabilities. The actual values that you see displayed here are just the density of the probability, not the probabilities themselves. It's a mysterious quantity to think about, and like all things in mathematics, when infinity gets involved, things get a little weird. So the probability density is often denoted with a lowercase letter. Frequently we use the letter f if we haven't used that already in an equation. And you can find the probability of values for your random variable. You say you're interested in a probability that x is between 0.6 and 7. So now we're going to be talking about the actual probability of an outcome because it's a range on the x-axis, a range of values. And technically the way you do that is you integrate the probability density from 0.6 to 0.7. Now don't worry, we're going to use pre-calculated tables in this course. You're not going to have to do these integrals by yourself, and in fact a lot of the integrals we use in even basic statistics are extremely difficult integrals to do analytically, but fortunately statisticians have already looked up the values for them. So we don't have to do the mathematics of the integration, but it's really important that you understand and have in your head the idea that when you see a probability density curve, it's depicting how much probability per unit. It's not probability itself, but probability density, and when we make probability statements, we're making them about regions of that curve. Okay? And so when we're talking about this situation where we have continuous variables, Rule 1 and Rule 2 get modified a little bit. The probability density is always non-negative, but it can be greater than 1. You may notice that on this slide here. This is not an error that the probability of density is 8. The probability density can indeed be greater than 1 because it's not a probability. It's just how much probability per unit of the x-axis. And so now instead of saying we sum all the events to get the probability that equals 1, now we're doing an integral of the entire range, the entire sample space. So if it's a numerical variable that can be negative, from negative infinity all the way up to positive infinity, that integral will equal 1. So it's kind of the continuous analog of doing a summation. And another thing that is easy to get confused about is because there's no probability for any single point on the number line, right? Every point has got a probability of 0 and may have some probability density, but no probability. If we're dealing with a continuous random number, the probability that it's between, say, 0.6 and 0.7, including those endpoints, so less than or equal to, in both cases, that's actually the same probability as if we just say what's the probability it's less than those bounds. Because the 0.6 itself and the 0.7 itself contribute no probability, sometimes it'll look like we're being really sloppy with the less than or equal to or greater than or equal to and just replace it with a greater than symbol or a less than symbol. But that's actually not sloppy. It's allowed because in this case there is no probability with those endpoint values, so that you get the same probability because it's the same region that we're talking about. Okay, that's going to be important to bear in mind as we move on in the course as well. So that's the end of this video. Next video we're going to talk some about joint probabilities, the probability of two different things happening on the same trial. All right.